Let us continue exercise 1.1. Question number 9. Show that each of the relation R in the set A, set of all x belonging to Z such that 0 less than or equal to x less than or equal to 12, given by the relation R, set of all a comma b such that modulus of a minus b is a multiple of 4. We have to show that it is an equivalence relation. So let us first check whether it is a reflexive relation or not. So if I consider a comma a, absolute value of a minus a is 0 and it is a multiple of 4. So I can say that a comma a belongs to R for every a belonging to capital A. So in capital A we have set of all integers 0, 1, 2, 3, etc. up to 12. So it is true for all the elements belonging to A, therefore we can conclude that R is reflexive. Now the second one. Let us consider AB belonging to R, which implies A minus B is a multiple of 4. If modulus of A minus B is a multiple of 4, definitely modulus of B minus A is also a multiple of 4, because modulus of A minus B and modulus of B minus A are same, which implies B comma A belongs to R, and it is true for two elements taken from the set A. Therefore, R is symmetric. Now the third one. Let us consider two elements AB and BC. Remember, this element should be a common element for transitive relation. Belonging to R implies modulus of A minus B and modulus of B minus C are multiples of 4. So to get A minus C, I have to add them. But we know that modulus of x plus modulus of y is not equal to modulus of x plus y. We cannot add like this. We have to remove the modulus sign to add. So I am taking, since it is a multiple of 4, I can write it as 4m. And this is also a multiple of 4. Let us take it as 4n. I am removing the absolute value sign. So to remove the absolute value sign, I can write plus or minus sign. And similarly, B minus C is plus or minus 4n. Now let us add these two equations. A minus B plus B minus C is plus or minus 4 times m plus n. Therefore, modulus of A minus C is 4 times m plus n, which is a multiple of 4. Since it is a multiple of 4, I can say that it belongs to the relation R. So A comma C belongs to R, and it is true for A, B, C from A. Therefore, R is transitive. We have proved that R is reflexive, symmetric as well as transitive. Therefore, I can say that R is an equivalence relation. Now we have to find the set of all elements related to 1 in each case. So the set A is 0, 1, 2, 3 up to 12, all integers from 0 to 12. Now we have to write the elements which are related to 1. That is nothing but the equivalence class of 1 we have to write. So 1 is related to 1 because 1 minus 1 is 0, which is a multiple of 4. And 1 is related to 5 because 1 minus 5 is 4, which is a multiple of 4. And then 1 is related to 9 because the difference again is 8, which is a multiple of 4. So 1 is related to 9. So 1 1 will be in R and 1 5 will be in R. 1 9 is also in R. Therefore, we have written the equivalence class of 1, or the elements which are related to 1 are nothing but 1, 5 and 9. If we write the equivalence class of 5, you will have the same 3 elements. Equivalence class of 9 also will have the same 3 elements in this case. So this is the answer. Now the second subdivision. The given set A has integers from 0 to 12. And the relation R is defined as set of all A, B such that A is equal to B. This is an easy question. Let us check. Let us prove that it is reflexive. So A is equal to A we know. Therefore, I can say that A, A belongs to the relation R for every A belonging to the given set A. Therefore, R is reflexive. Now the second one. Let A, B belongs to R, which implies A is equal to B by the definition. If A is equal to B, I can very well write B is equal to A. Therefore, B, A belongs to R for AB belonging to A. So I have proved that if AB belongs to R, BA belongs to R. Therefore, R is symmetric. Let us prove that it is transitive. For transitivity, we have to take two elements such that these two are common. Now, AB belongs to R, so the condition is A is equal to B. And BC belongs to R, the condition is B equals C. Therefore, I can say that A is equal to C. That means A, C also belongs to R for three elements A, B, C taken from the set A. Therefore, I can conclude that R is transitive. Now, all three conditions are true. Therefore, we conclude that R is an equivalence relation. Okay, now find the set of elements related to 1 in this case also. So the elements related to 1 will be 1 only, because 1 is related to 1, 1 is equal to 1. We cannot have other elements. So this is the answer. Question 10. Give an example of a relation which is, okay, we will take the given set as 1, 2, 3. A symmetric but neither reflexive nor transitive relation we are going to write. So it should be symmetric. I will take 1, 2, let me name it as R1, 1, 2 and 2, 1. I have taken 2 elements. This is a subset of A cross A. A cross A will have 9 elements. Okay, out of those 9 elements, I have taken 2 elements. And this is symmetric because 1, 2, 2, 1 are there, but not reflexive. So not reflexive, the reason is 1, 1 doesn't belong to R1. Therefore, R1 is not reflexive. Now it is symmetric. We can show that it is symmetric easily. 1, 2 belongs to R implies 2, 1 belongs to R. Or if you take 2, 1, 1, 2 belongs to R. So I can say that 1, 2 belonging to R1 implies 2, 1 belongs to R1. Similarly, the other way around. 2, 1 implies 1, 2 belongs to R1. Therefore, R is symmetric. Now let us show that it is not transitive. 1, 2 and 2, 1 they belong to R1. But 1, 1 doesn't belong to R1. See, for transitive condition, these 2 elements are common, but you have to check for AC. 1, 1 doesn't belong to R1. Therefore, R1 is not transitive. So we gave one example which is symmetric, not reflexive, and not transitive. Now the second example, let me name it as R2. I have to give a transitive relation, but neither reflexive nor symmetric. Okay, let me take 1, 2, 2, 3 and 1, 3. So it is not reflexive because 1, 1 is not there, because the given set has 1, 2, 3, right? It doesn't belong to R2. Therefore, R2 is not reflexive. Okay, now let us check whether it is symmetric or not. 1, 2 belongs to R2, but 2, 1 is not there. Therefore, R2 is not symmetric. Okay, let us check the transitive condition 1, 2, 2, 3. They belong to R2. And look for 1, 3. Check. Yeah, 1, 3 is also there in R2. Therefore, check the other elements. 2, 3, 3, starting with 3, we don't have other elements satisfying A, B, B, C condition. Okay, this is satisfied, therefore R2 is transitive. So we wrote an example which is transitive, but neither reflexive nor symmetric. Now the third example, we'll take the same set A, which is 1, 2, 3. Let me take R3 as I have to write a reflexive and symmetric but not transitive relation. Okay, it should be reflexive. Since it should be reflexive, for all 3 elements I should have AA form. 1, 1, 2, 2, 3, 3, which makes it reflexive. And it has to be symmetric. This is symmetric, not transitive. If I leave it like this, it will become transitive because we don't have elements of the form A, B, B, C. Or 1, 1, 1, 1 only we have to take. Okay, now let me add few more. 1 2 2 1 because I have to make it symmetric, and 1 3 3 1. Out of 9 elements of A cross A, I have written 7 elements. So it is reflexive, it is symmetric, but not transitive. See, AA belongs to R3 for all A belonging to A. Therefore, R is reflexive. Now, if AB belongs to R3 is reflexive. Okay. We can say that BA is also there. 1 2 2 1, 1 3 3 1 belongs to R3 for any two elements of the form AB belonging to A. Therefore, R3 is symmetric. But check, give a counter example to show that it is not transitive. 1 2 1 and 1 3. See these elements? 1 is a common element. They belong to R3, but 2 3. AC you have to check. 2 3 doesn't belong to R3. Therefore, R3 is not transitive. That's it. We have to give an example which is reflexive, symmetric, but not transitive. Now, fourth, we'll use the same set 1 2 3, and we have to write a relation which is reflexive, transitive, but not symmetric. Let me take this as R4. It should be reflexive. Of course, I have to write 1 1 2 2 3 3 to make it reflexive. Okay, and transitive. If I leave it like this, it will be transitive and not symmetric. It becomes symmetric also. Okay, let me add one more element, 1 2. Now check. So I will write A comma A belongs to R4 for all A belonging to A. Therefore, R is reflexive. And then 1 2 belongs to R4, but 2 1 doesn't belong to R4. Therefore, R4 is not symmetric. Okay, transitive, yeah, 1 1 1 2. 1 2 is there. And if I take 2 2, we don't have any element starting with 2 to check. And 3 3, there is no other element starting with 3. I have to check with only 3 3 and 3 3. Okay, so it becomes transitive in that case. Therefore, I can conclude that R4 is transitive. Then if we take 1 2 and 2 2, 1 2 is there. So we have written an example which is reflexive and transitive but not symmetric. Now fifth example. Symmetric and transitive but not reflexive. Let me name it as R5. It should be symmetric. 1 2 2 1. Let me take 1 1 and 2 2. 4 elements I have taken. It is symmetric. See, 1 2 2 1. So R5 is symmetric and transitive also. Because if I take 1 2 and 2 1, 1 1 is there. Even if I consider 2, 1 and 1, 2, if I interchange both the elements, 2, 2 is also there, okay, which makes it transitive, but not reflexive, because 3, 3 is not there. 3, 3 doesn't belong to R5, therefore R is not reflexive. Here 3, 3 doesn't belong to R5. Please change it. Question 11. Show that the relation R in the set A. A is the set of all points in a plane. Now the relation R is defined as set of all P, Q such that distance of the point P from the origin is same as the distance of the point Q from the origin. That means OP equals OQ, where O is the origin. Instead of writing the whole sentence, I have written OP equals OQ. Okay, we have to show that it is an equivalence relation. Equivalence relation is a relation which is reflexive, symmetric and transitive. So I can say that OP equals OP for any point P. So I can say that P, P belongs to R for any point P taken from the set A. We denote the points by capital letters. That's why they have written the capital letters. Therefore, R is reflexive. Now let us take P, Q element of R, which implies OP equals OQ by the definition. If OP equals OQ, I can very well say that OQ is equal to OP, which implies Q, P belongs to R for any 2 points taken from the set A. Therefore, R is symmetric. Now let us take PQ and QS we will take. These are the 2 elements of R, say. See, Q and Q, common elements I have taken, which means OP and OQ are equal and OQ and OS are equal. So which implies OP equals OS. Therefore, I can say that P, S is an element of R for the 3 points P, Q, S taken from the set A. Therefore, R is transitive. Very simple question. So all 3 are true. It is reflexive, symmetric as well as transitive. Therefore, I can say that it is an equivalence relation. Now the second part of the question is, further show that the set of all points related to a point P, which is not the origin, is a circle passing through P with origin as the center. For example, this is the y-axis and this is x-axis. Say P point is here. The distance, let OP is the distance between the origin and P point, say. So the points which are related to P are at the same distance from the origin, like P. So if I join all those points which are at the same distance OP, then I get a circle whose radius is OP and the center is O. So the points which lie on this circle are related to the point P. Right, therefore, the set of all points related to P, which is not the origin, is the circle passing through P with origin as center and radius OP. Question 12. Show that the relation R defined on the set A of all triangles. A is the set of all triangles. And the relation R is set of all T1, T2 such that T1 is similar to T2. Show that this is an equivalence relation. First one, I can say that T1 is similar to T1. Any triangle will be similar to itself. Therefore, we conclude that T1, T1 belongs to R. And it is true for any triangle taken from the set A. Therefore, R is reflexive. Now let us take an element T1, T2 from this relation R, which implies T1 is similar to T2. So if T1 is similar to T2, I can very well say that T2 is also similar to T1. Therefore, T2, T1 belongs to R for T1, T2 belonging to the set A. Therefore, I can conclude that R is symmetric. Now the third one, let us take T1, T2 and T2, T3. That's how we take for transitive relation, which implies T1 is similar to T2 and T2 is similar to T3, which implies T1 is similar to T3. Therefore, T1, T3 belongs to R. And this is true for any three elements taken from the set A. Therefore, R is transitive. So all three are true. Therefore, it becomes an equivalence relation. Equivalence relation. Now the second part of the question is, they have given three triangles. T1 triangle is with sides 3, 4, 5 and T2 triangle is having sides 5, 12, 13 and T3 is the third triangle with sides 6, 8 and 10. Which triangles among T1, T2, T3 are related? Here the relation is similarity. Which two triangles are similar we have to see. Now see the ratio of T1 and T3. The sides are proportional. All these three ratios are same. So I can say that T1 is similar to T3. That means T1 is related to T3. Question 13. Show that the relation R defined in the set A of all polygons. So A is set of all polygons. and R is set of all P1, P2 such that P1 and P2 have same number of sides. Show that this is an equivalence relation. I can say that P1 and P1, same figure, definitely will have same number of sides. Therefore, P1, P1 belongs to R, and it is true for any P1 taken from the set A. Therefore, R is reflexive. Now the second condition, let us consider P1, P2 is an element of R, which implies P1 and P2, they have same number of sides. If P1 and P2 have same number of sides, P2 and P1 also will have the same number of sides. Therefore, P2, P1 belongs to R, and these two are taken from the set A. Therefore, I conclude that R is symmetric. Now we have to prove the transitivity. For transitive condition, we know how to take two elements, P1, P2 and P2, P3. These two elements should be common. They belong to R, say. That means P1 and P2 and P2 and P3 have same number of sides. So P1 and P2 are having same number of sides. P2 and P3 are also having same number of sides. That means P1, P3 have same number of sides. Which implies P1, P3 belongs to R. For three elements P1, P2, P3 taken from the set A. Therefore, R is transitive. All three conditions are true, so we conclude that R is an equivalence relation. Now the second part of the question is, what is the set of all elements in A related to the right angle triangle T with sides 3, 4 and 5? Triangle has 3 sides. So the figure should have the same number of sides. That means set of all triangles. So the elements in A related to the given triangle are, so the elements in A related to the given triangle are all triangles. The answer is set of all triangles. Question 14. L is the set of all lines in XY plane and R be the relation in L defined as L1 comma L2 such that L1 is parallel to L2. Show that R is an equivalence relation. This is a very simple question. So I can say that L1 is parallel to L1, and it is true for any L1 taken from the set L. Therefore, R is reflexive. Now the second one, L1, L2 is an element of R, say. The definition is L1 must be parallel to L2. If L1 is parallel to L2, L2 will be parallel to L1. Therefore, I can say that L2 comma L1 will also be in R for any two elements L1 comma L2 taken from the set L. Therefore, R is symmetric. The third one, let us take two elements L1, L2 and L2, L3 belonging to R. That implies L1 is parallel to L2 and L2 is parallel to L3. See, L1 is, this is L1, parallel to L2, and L2 is parallel to L3. So I can say that L1 and L3 are parallel, which implies L1 is parallel to L3, which implies L1 comma L3 belongs to R for the three elements L1, L2, L3 taken from the set L. Therefore, R is transitive. So all three conditions are true. Therefore, R is an equivalence relation. Now the second part of the question is, find the set of all lines related to the line y is equal to 2x plus 4. For example, y is equal to 2x plus 4 is this line, say. This is y is equal to 2x plus 4. The lines which are related to this are all parallel lines, parallel to this. How many such parallel lines we can draw? Infinitely many. So we know that the equation of set of parallel lines, only they differ by the constant term. So I can say that y is equal to, slope will be the same, no? For all the parallel lines, slope is the same. So y is equal to 2x plus the constant term will be different for parallel lines. And C can take any real value. So this represents the set of all lines related to y is equal to 2x plus 4. So the set of all lines related to the line y is equal to 2x plus 4. Question 15. R is the relation defined on the set 1, 2, 3, 4, and the relation R is given as 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, and 3, 2. Choose the correct answer. Okay, look at this. The given set has 4 elements. So 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is also there. So it becomes a reflexive relation. It is reflexive. Now, it is not symmetric. 1, 2 is there, but 2, 1 is not there. Therefore, not symmetric. So not symmetric, definitely first subdivision is not true because it is given symmetric. And reflexive transitive condition. So we have to check whether it is transitive or not. 1, 2. If I consider the element 1, 2, check with the element starting with 2, 2, 2. So 1 2 is there. Then starting with 2, no element 1 1 1 1 1 2. It is transitive, so you can check for all possible elements. 1 3, starting with 3 I have 3 3, so 1 3 is there. For 1 3 and 3 2, 1 2 is there. So check for all possibilities. Okay, transitive condition takes time to check. So it is transitive. You have to check for all possible elements. Therefore, B subdivision is the correct answer. Now question 16. The relation is defined on the set N, and the relation is given as set of all A, B such that A is B minus 2 and B is greater than 6. We have to check which answer is satisfying this. 2, 4. No, B is not greater than 6. B is 4. So first one is not true. Now the second one. 3, 8. B is greater than 6. But what about A? 3 should be equal to 8 minus 2. No, they are not equal. 6, 8. Yeah, 8 is greater than 6. And 6 is equal to 8 minus 2. Both the conditions are satisfied. Therefore, 6, 8 is the answer. And what about 8, 7? Let us try that also. B is greater than 6. But 8 is not equal to 7 minus 2. So C is the correct answer.